Okay, we are gonna work on the model of Wound Rotor Induction Machine. And in this video we are gonna figure out the stator and rotor voltage. Okay, so before we start, just a little background into Wound Rotor. So first we are gonna have what is synchronous speed. So synchronous speed is the physical speed of the rotation of the rotating magnetic field. Okay, so that sounds like a tongue twister, but it's like this. Let me draw here a circle. We are gonna have the stator on the outside, and we are gonna have the rotor on the inside. Okay, so the stator does not move, but the rotor move. Now we know that there's gonna be coils in the stator, and we are gonna have coils in the rotor too. So as the polarity of the magnetic field in the stator changes, so this point will not move in space, but is the current that we are passing, it is moving in electrical. So if we here we have 0, we have pi and 2 pi. Sorry, we have 0, 180 and 360. So we know that when the current gets into 180, this is gonna be a dot. So that's how the magnetic field is rotating, like this. And as the magnetic field rotates, this one is gonna try to follow mechanically, is gonna rotate and try to follow that. So the speed at which the magnetic field is rotating is what we call the synchronous speed. So we know that for this we can see that in an electrical cycle uh, is gonna be 380, but for when we turn 360 or 180 here to get to the negative, this one is just gonna move 90 degrees. So for every 380 degrees of electrical, we are gonna get 180 degrees in the mechanical. So and that's for 4 poles, like we can see here that we got 4 poles. So this is one pole, this is another, and another. So we got 4 poles. So we got 4 poles. We know that this should be 360, so we have to divide this by 2, and we know that in the mechanical we got 180. So if we write this as an equation, we will get that the number of poles divided by 2 times the mechanical is gonna give us our electrical. So if we turn this into speed, it's gonna be number of poles times 2 times the speed in mechanicals, and this is gonna be radians per second. Okay. So we know that speed is 2 pi f, the frequency, the angular frequency, and we're gonna have that is equal to number of poles over 2 in the mechanical. So our mechanical, our speed in mechanical is gonna be equals to 4 pi times the frequency over the number of poles, and this is in radians per second. So if we want to change this into speed in RPMs, that is actually our synchronous speed ns. We are gonna have 4 pi frequency over the number of poles, and we multiply by 60 over 2 pi. That's to change to RPM. and we are gonna have that our synchronous speed is equals to 120 times the frequency over the number of poles, and this is gonna be in RPM. Okay, so as an example, if we have a frequency of 50 hertz and 2 poles, and then we are gonna know that our synchronous speed is gonna be 120 times 50 over 2, and that's gonna give us 3000 RPMs. Okay, so that is synchronous speed, and that's the, and we are gonna model the the voltage. We are gonna derive the voltage equations for the stator and the rotor for this machine. So let's look at what the machine will look like in terms of the coils. So the black ones are gonna be our stators, and the red ones are gonna be our rotors. Okay, so in a previous exercise we figured out that if we wanted to find a mutual inductance between two coils of the same, so between the coils of the stator, we figured out that this is equals to the peak number of turns square times the permeability over the radius times the length of the conductor over the air gap pi cos 2 pi over 3. And we found that the mutual inductance, the the self-inductance, yes, the magnetizing is gonna be equals to mp squared mu naught rl over g times pi. And this is for, yes, so these are gonna be our uh, mutual inductance and our magnetizing inductance. Okay, so if we translate this into our inductance for our coil AS with respect to AR, we're gonna have that instead of ampere square, we're gonna have ampere times amps mu naught RL over G times pi. And this multiplied by the cosine of the angle epsilon that we got here. So it's gonna be like our mutual inductance, but when we have R here, and we know that this is 120, so that's why this is 2 pi over 3. But in this case we have epsilon. And we are gonna have that. And we are gonna call LSR all of this. That's just so we don't have to write it over and over and over. So the inductance between AS and AR, sorry, is gonna be LSR cosine of the angle epsilon. Okay, so if I know I'm going a little bit quick here, but that's because in other videos we have done this before when we had an exercise of 3 phases. Okay, now we have to figure out the voltage in AS here, the voltage in AS. So like in the video that we had with 3 phrases, we know that we are gonna have here a resistance R1 for the line, this phase is gonna have a resistor side 1. So we know that we're gonna have, and we know that the current that is going through here, we are gonna call IS. So we are gonna have IS that multiplies R1. Okay, and we are gonna say that this resistance is gonna be the same for all of our phases in the stator. Now we need to find the mutual inductance. We need to find the mutual inductance between each one. So we already did one for B, and we said that's gonna be m cos 2 pi over 3. So the mutual inductance between A and B, cos of the angle. So we know that between between A and IB we have 120 degrees, and we derive by the current in B because we are considering what is induced by B. So, and we know that M is this, what we already calculated. And then we keep going, and we're gonna do the same for C. So we are gonna still have M cos, and here we're gonna have the derivative of ICS, and the angle between A and C is gonna be 240. So we write here 5 pi over 3. Now comes the LSR. We know that we're going to have cos of an angle, and we're going to start with IR, so the derivative of IR. So the angle between A and AS and IR is epsilon. So here we have epsilon plus LSR cosine of, we know that we are going to have epsilon, and let me see if it's plus or minus, and we know that we are gonna have the derivative of IBR. So the distance between IS and IBR is gonna be this angle epsilon, and it's gonna be plus 120 degrees. So it's gonna be plus 2 pi over 3. Okay, and finally we're gonna do the same for the last one. So it's gonna be LSR cos of epsilon plus minus something. We're gonna figure that out. And the derivative of ICR. Now, ICR is epsilon and 240 degrees from AS. So we're gonna have 240, so 4 pi over 3. Okay, so this is gonna be our voltage equation for our, our phase A in the stator. Now, we know that another way we can represent this is going to be voltage, the number of times, number of turns the phi dt, where phi is the flux. So n times flux is going to be our flux linkage. And we know that we got an inductance that is equals to the flux linkage over the current. So if we have the inductance and we multiply by the current, we are going to get the flux linkage. So another way of writing this could be the voltage in AS is going to be equals to R1 is plus we have flux linkage when we have the inductance times I. So we are going to have the derivative of our total flux linkage in our phase A. Yeah, so remember this is total flux linkage. So what would be our total flux linkage in phase A? Well, it's gonna be the multiplications of our inductances times the current. So we got, for the first one is gonna be Ls. Now Ls is gonna be our self-inductance of the coil. So Lx is gonna be the magnetizing plus the self-inductance. So, and we're gonna call it ILS. ILIS. Okay? So this is just so we don't have to write this over and over. Okay? So we're gonna have LS times IS plus, so now we need to go through each of this. So we know that this, so it's gonna be the same than this, but instead of the derivative, we are just gonna have IBS, ICS. So it's gonna be the same. So we're gonna have M cos 4 pi over 3. I'm sorry. 2 pi over 3. This was 2 pi over 3, yes. And we multiply by our current IBS plus N cos 4 pi over 3. And we multiply by our current ICS. Okay. Let me make this a little smaller so everything can fit. And also I'm gonna show here a grill so I stop writing down words. Okay. So this is gonna be for this stator. Now we have to do the same for the uh, rotor. So we are gonna have LSR cos of epsilon plus 2 pi 3 IPS. And again, this is just the same that we had here. Oh, well, I started with IBS, but we need to start with LSR times cos epsilon of IR. Okay, now we can have IPS and then we can have LSR cos of epsilon plus 4 pi over 3 ICR. Okay, so we got our equation for our total flux in A, and we can do the same to find our total flux in B. So just like this one is going to be LS IBS plus M cos of an angle IBS. Okay, well, let me write it in another order. So So we have all the IAS here. That's gonna make things a little simpler in a moment. So we're gonna have that M cos of an angle IAS. So between BS and IS, we have 120 degrees. So that's what we're gonna put here, 2 pi over 3. Plus, now this is ls because we are with respect to b. So it's gonna be ls IBS plus m cos of an angle ICS. B and C is 120 degrees apart too. So it's 120 degrees, but this one is minus here. So it's gonna be, oh no, it's just 120 degrees. Okay, ICS plus LSR cos of epsilon, probably an angle IAR. So what this angle, where is this angle going to be? So we have here BS and here we have ISR. So in this case we know that we have epsilon here, yes. So if we take epsilon minus 120 degrees, we're gonna get this angle. Okay, so it's gonna be minus 2 pi over 3. Okay, let me make this smaller so it fits. Okay, so the other one is going to be LSR cos epsilon and angle IBS. And for this one, we know that from here to here is epsilon. So we actually just need epsilon here. Plus LSR cos of epsilon and angle ICR. So we know that from here to here is 120 plus epsilon. So 2 pi over 3. Okay. And finally, we do the same for, remember, all of this is for the stator. So the total flux linkage in our phase C. So again, we are going to have M cost of an angle IAS. Okay. So what angle we have between C and A is 240. So 4 pi over 3 plus M cos of an angle IBS, and well, we know that we have 220 degrees between IBS and C. So and we have the self-inductance, so we're gonna have LS ICS. Okay, so let me make this smaller to make space. Okay, plus LSR cos of epsilon, probably an angle IR. So let's see. We are gonna have 240 minus, well, we're gonna have epsilon minus 240. So 4 pi over 3 plus LSR epsilon. And if we keep going like this, we know that this is going to be 2 pi over 3 IBR. Okay, let's make this smaller so it fits. And we are going to have here LSR cos of epsilon ICR. Why epsilon? Because between these two, we got epsilon. Okay. Now that we got our total flux linkage, we can apply Clark's transformation. Okay, so we are gonna have the Clark transformation that we have done many times before. That is our phasor in A minus 1/2, our phasor in B minus 1/2 in C. Okay, so this is gonna be equals to R1 IS1 plus the derivative of the total flux linkage in IS minus 1/2 R1 PS minus IPS minus 1/2 the derivative of the total flux linkage in PS, and we're gonna have minus 1/2 R1 ICS minus 1/2 the derivative of the total flux linkage in CS. Okay. And all of this, if we collect the terms, is gonna be equals to R1. If we collect all of our R1s, we're gonna have that R1 is gonna be equals to I times IAS minus 1/2 IPS minus 1/2 ICS. And in the derivative, if we collect it, we're gonna have the total flux linkage in IS minus 1/2 our total flux linkage in PS minus 1/2 our total flux linkage in CS. Okay. And this is, we know that this is our alpha component, and this is also our alpha component. So our alpha component in BS is just going to be equals to R1, our alpha component of the stator, plus the derivative of the alpha component of the total flux linkage in the stator. Okay, so from here we figure out that our alpha component of the total flux linkage in the stator is gonna be equals to our total flux linkage in phase A of the stator minus 1/2 over phase C minus 1/2 over face B, I'm sorry, and face C. Okay, so this is gonna be equals to, we have already figured out these values, so just gonna copy them. So this one minus 1/2 this one minus 1/2 this one. Okay, now if we collect terms, okay, so let's start collecting our currents. Let's start with IIS. So we know that here this one have LS, and we are gonna have minus 1/2. This one is gonna be m cos 4 pi over 3. Oh wait, I skipped this one, so this one is gonna be here, and here we're gonna have minus 1/2 m cos 2 pi over 3, and then we are gonna have this one, minus 1/2 cos 4 pi over 3. Now let's collect our IPS. There's gonna be one here, so we are gonna have m cos 2 pi over 3 minus 1/2 ls minus 1/2 m cos 2 pi over 3. Okay, so that's gonna be our IPS. Now our ICS, we have here m cos 4 pi over 3. So I'm just gonna copy them. It's a lot faster. Minus 1/2. Here we have ICS, here we have ICS, so collect this one too. Minus 1/2 ls. Okay, this one I can write ls. Okay, now we are gonna have IR, and IR we have here. Okay, we can collect this IR. So ls R cos of epsilon minus 1/2. So we collected this. ls R cos epsilon minus 2 pi over 3 minus 1/2. So this one is the one, and we have this one. LSR cos of epsilon 4 pi over 3. Okay, the same for IBR. So we have IBR here. So we take all of this minus 1/2 this minus 1/2 this, and finally we do it for ICR. So we just collected this and this, so ICR is gonna be this minus 1/2 this minus 1/2 this. Okay. Okay, now we can start simplifying. We have that IAS. So we are gonna have this ls cos this is gonna be minus 1/2 um, minus 1/2. So we have ls plus n over 2 plus IPS. So it's the same. We just plug in the calculator and figure out what this value is gonna be. So minus ls over 2 minus n over 4. Now we have ICS minus ls over 4 minus m over 2. Okay, and for the other part we're going to have the IR. It's going to be 3/2 cos epsilon LSR. So what we have is here, simplifying all of this. To simplify all of this, I just use MATLAB because I wasn't feeling like writing the whole thing. But yeah, I just use MATLAB and I got this. 3 pi cos LSR. The same for IPR. We're going to have minus 3/2 cos epsilon minus pi over 3 LSR. And we are going to have ICR multiplying minus 3 pi over 2 cos of epsilon plus pi over 3. Okay. Now we can keep simplifying. So we know that we have ls plus n over 2 here. So if we factor this out, we're gonna have that we're gonna get is. When we factor this out from here, ls, wow, this is for idea. So now when we do it from here, we're gonna have that this is gonna be minus 1/2 IBS when we factor out LSM from this. And then we're gonna get minus 1/2 again when we factor out from here ICS. Okay. If we will look at this, we know that this is our alpha component. Now for our IR is gonna be equals to IR. We still have the 3/2 cos epsilon LSR, how much we can do here. Oh well, here I just simplify the top part. So now if we simplify the bottom part, we can factor out 3/2 LSR because that's in every term. Here also LSR. Okay, so we are gonna have 3 halves LSR, and we're gonna have IAR cos of epsilon minus IBR cos of epsilon minus pi over 3 minus ICR cos of epsilon plus pi over 3. Okay, now we need to find a way to separate this, so we are gonna do the identities that say that cos I minus b is equal to cos times I times cos of b, because if this is minus, we are gonna have here a plus sine I and sine b, and the other side of this is we have a plus here, and it's gonna be cos A times cos B minus sine A times sine B. So if we apply this for this, well, first of all, up here we are gonna get that this is our alpha component, so we are gonna have ls plus lm I alpha s, and down here we are gonna have 3 halves lsr multiplying what? This one stays the same, cos epsilon minus IBR that multiplies cos of epsilon times cos of pi over 3 plus sine of epsilon times sine of pi over 3. Okay, and we are going to have minus ICR that multiplies cos of epsilon times cos of pi over 3 plus sine of epsilon times sine of pi over 3. Okay, so here we still have our ls plus m I alpha s, and down here LSR 3 half LSR, so this one doesn't change, IR cos of epsilon A minus IBR multiplying cos of epsilon times 1/2 plus sine of epsilon times square root 3 over 2 minus ICR multiplying cos of epsilon times 1/2 minus sine epsilon square root 3 over 2. Okay, so from this we just calculated the ones that we could. So we are going to have ls plus lm I alpha s plus 3 half LSR that multiplies. Okay, now we can collect our terms. So let's collect our cosines. So cosine epsilon. And our cosine epsilons, we're going to have here IR. Here we have another cosine epsilon, so it's gonna be minus 1/2 IBR. And here we have another cosine, so it's gonna be minus 1/2 ICR. Okay, and now if we collect our signs, minus sign epsilon. So if we collect minus sign epsilon, we're gonna have here IBR. We connecting the minus. Well, we're gonna have square root 3 over 2 IBR right here, and we're gonna have minus square root 3 over 2 ICR. Just be very careful with the signs and everything. That's like the hardest part of this. So now we know that this is our alpha or beta component in a rotor. So our alpha component in our stator is going to be equals to ls plan plus m times our alpha component of the stator plus 3/2 lsr, and we know that this is our alpha component. So let me move it a little bit down so it doesn't crash. Okay. So we are gonna have cos epsilon and our alpha component in the rotor minus sine epsilon and our beta component in the rotor. Okay, so this is our total flux component alpha component in the stator. We need to do the same, find the beta component of the total flux in the stator. So we know that the transformation is square root 3 over 2. Our component our B minus our C. So that's right what we have here. So again, we are gonna have square root 3 over 2 multiplied our B. If we go back here to where we found our equations, so multiply our B. Okay. Multiplying our B. And we are going to have minus square root 3 over 2 multiplying our C. And if we go back, this is our C. Okay. So again, we collect terms. So let's collect square root 3 over 2 IAS. So we are going to have this one minus this one. Okay. Those are two IAS. Now if we collect our PS, IPS, again, it's going to be square root 3 over 2 IBS. So it's going to be LS it's going to be LS minus, well, yeah, they actually fit, so I'm going to put it like this to have again our, and we're going to have here minus this part. And finally, we're going to have square root 3 over 2, and we're going to collect our IS. So we're going to have this minus LS. Okay, and now we can collect our IR. So square root 3 over 2 IAR is going to be this minus this. Plus square root 3 over 2 IBR. So IBR, this is our answer. It's going to be this minus this. And finally, this is all adding this part up here, plus square root 3 over 2 ICR, and it's gonna be this let me just make the whole thing a little smaller. Okay, this minus this. Okay, so we can actually calculate for the part upstairs. So we're gonna have square root 3 over 2 IAS multiplying 0, that's the result of this, plus square root 3 over 2 IBS times LS plus n over 2, that's the result of this, plus square root 3 over 2 minus m over 2 minus ls, and that's the result of this. Okay, so now we go with this part, so plus square root 3 over 2, gonna factor out the lsr2 ir, and now we are gonna apply the same trick identity that we did here for each one of this. So we are gonna get cos epsilon times cos 2 pi over 3 plus sine epsilon times sine 2 pi over 3, all of this minus, so this is this part, now we are gonna do, sorry, this is this part, and now we are gonna do this part. So we have minus cosine epsilon times cos 4 pi over 3 plus sine epsilon times sine 4, okay, let me write it a little bit better, epsilon sine 4 pi over 3, okay, and this is our IR, so we're gonna do the next one, LSR, IPR. So for IPR we do the same, we're gonna get cos epsilon, this one is gonna be alone because here we only have epsilon, now minus, okay, this is cos, oh no, didn't write it all, okay, so we're gonna have minus cos epsilon times cos 2 pi over 3 plus sine epsilon, so sine 2 pi over 3, and this is gonna be our IPR. And finally we do it for our LSR ICR. So we apply the same, cos epsilon times cos 2 pi over 3 minus sine epsilon times sine 2 pi over 3, and here we only have cosine epsilon. So that's for this part. So in here we only had cos epsilon, so that's what we leave here. Okay, so again, for our first part, we can collect our ls plus m over 2, so ls plus m over 2, and when we do that we are gonna get square root 3 over 2 times IPS minus square root 3 over 2 ICS. Okay, so just look at this. When we factor this out, we are gonna get IBS, and when we factor this out from here, we are gonna get minus square root 3 over 2 ICS. Okay, and we know that this is our beta component. Okay, now for the rotor part, we have square root 3 over 2 IR LSR multiplying, we just do the ones that we can do, so 1/2 cos epsilon plus square root 3 over 2 sine epsilon plus 1/2 cos epsilon plus square root 3 over 2 sine epsilon. Okay, we're gonna have our square root 3 over 2 IPR LSR multiplying cos of epsilon plus 1/2 cos epsilon minus square root 3 over 2 sine epsilon. And finally, we're going to have square root 3 over 2 ICR LSR minus 1 half cos epsilon minus square root 3 over 2 sine epsilon minus cos epsilon. Okay, so what I did is just evaluate the ones that we could evaluate and write it down. So this is going to be equals to ls plus m over 2, our beta component of the stator. We're going to have plus square root 3 over 2 IR LSR multiplying square root 3 sine epsilon, and will be all of this evaluated, simplified. So all of this simplified. Okay, so again, to do this, I just use MATLAB. So you write the expression and then use the simplify function, and it will give you the simplified version of the function. Okay, so we're gonna have our other component here, IPR LSR multiplying 3 half cos epsilon minus square root 3 half sine epsilon plus square root 3 over 2 ICR LSR minus 3 halves cos epsilon minus square root 3 over 2 sine epsilon. Okay, and now that we have everything a little bit more simplified, we can start looking for ways to make it look like our beta component. So upstairs we still have L 1 over 2 I beta s plus. So if we look at all of this, they all have 3 halves. So I'm gonna factor out 3 halves and our sign, and this is times LSR2 because every term has it, and we are gonna have IR. So if we factor out the sign, we're gonna have IR here, because when we multiply this times this, it's gonna be 3 halves, and when we factor out the 3 halves, we only have IR minus, again here we're gonna have 3/4, so when we factor out the 3 halves, we're gonna have 1 half left, IBR, and similar with ICR, we're gonna have 1 minus 1 half ICR, and we know that this is our alpha component. Now we keep going and do the same for the cosine. So we're gonna have 3 halves cos epsilon LSR. So which terms have cosine? So IR doesn't have, so we start with this one. And if we factor out 3 halves from IPR, so we are gonna have square root 3 over 2 IPR. From here, we're gonna have minus square root 3 over 2 ICR. Okay, and we know that this is our beta component. So we can say that this is equals to LSM over 2 IBS plus 3 halves sine epsilon E over alpha component in the stator plus 3 halves cos epsilon E. Oh, remember, here we have, let me just move a little bit, LSR, don't forget. 3 half cosine epsilon LSR multiplying our beta component in the stator. Okay, and if we collect a little bit more terms, we're gonna have that our beta component in the stator is gonna be ls plus n over 2 I beta s plus 3 halves lsr, because both there has lsr, I alpha r. I'm sorry, this is not, this is r because we are in the rotor, no, the stator, and this is also r. I forgot here. Okay, so it's r sine epsilon e plus I beta r, okay, cosine epsilon e. So this is our beta component of the total flux. So back to the question. Okay, so we know that our component in alpha of the voltage in the stator is going to be R1 times our current, our alpha component of the stator plus the derivative of the total flux alpha component. So now we have now that we have found this, let's plug it here. So we're gonna have R1 alpha S plus TT of what we found over here, that is our alpha component. Just make it smaller so it fits on the screen. Okay, and the same way our beta component of the voltage in the stator is gonna be R1 or beta component of the current in the stator plus TT, what we just found out was our beta component. Okay, okay, so our phasor alpha beta in the stator is going to be equals to our alpha component of this in the stator plus J and our beta component of the stator. So if we plug this, we are gonna have that all of this plus J then multiply all of this. Okay, And now we can collect terms. So let's collect our R1s. So R1 is here, so I alpha S. Where else is R1? Is here, so you have plus J I beta S. Okay. Now another term we can collect there, Ls plus M over 2. Who has that? We have it here. I alpha S right here. And we have it here. But of course I cannot just get rid of the derivative, so this is the derivative. Okay. And now we can say that we have our I alpha plus our J beta in the stator. And nothing else has Ls plus 2n plus n over 2. And now we can collect the rest of the derivative. Well, let me see what else can we factor. We know that, okay, all of these have 3 halves LSR, so we actually can get 3 halves LSR. And now we have the derivative, and what terms have 3 halves LSR? We have this, this, okay, could be funny. We're gonna have this plus J that multiplies this. Okay, so we're gonna have R1, so this is gonna be our phasor, the stator. Here we have plus Ls plus n over 2. Again, this is our phasor stator, and we're gonna have plus, let me write it right here, 3 halves. So this plus, I'm just gonna move it down so I have more space. LSR dt. Okay, so let me collect our I alphas. So I alpha R is here with a cosine epsilon E, and is here with a J sine epsilon E. And now let me collect plus J I beta R. So ij beta R here is negative. Okay, and the sign does not have I. So if we want to get minus 1 when we have J, we have to multiply by J. So J times J is gonna be minus 1. So this is gonna be sine epsilon plus, and we are gonna have here cos J cosine epsilon, but because we have factorial J, it's just cosine epsilon. Okay, so I'm just gonna write it here. J times j equals to -1. Okay, so we have what we already figured out here. We're gonna have plus 3 LSR dt, and now this and these are the same terms, so we can factor out I alpha r plus j beta r that multiplies cos epsilon e plus j sine e. Okay, so again we are going to have this plus 3 halves LSR. Now we're going to have dt, and we know that this is our phasor in the stator, and this is j e to the j epsilon. And this makes a lot of sense because when we started, we figured that for going to the this is a lot. We wanted to go from the stator to the rotor. We added an angle. So here we have the stator phasor, and we have to add an angle to get the rotor reference frame. So this is our equation for the voltage in our stator. And now we have to do the equation for the voltage in the rotor. Now we are going to have very similar things. So we are going to have the voltage here. We have a resistance, so we have R2, IR, because this is the current IR, plus the derivative of the total flux linkage in IR. And it's going to be the same for BR, R2, because they all have the same resistance, BR, and this time is the total flux linkage in BR, and the same for CR, R2 square, IPR, plus dt CR. Okay, so if we look at this, IR is just 100, is just epsilon from IS. So if we are calculating the mutual inductance between its own phases, is gonna be the same that when we calculated for IS. So when we get our voltage equation for BR, we're gonna have R2, our phasor in R, plus LS plus N over 2 dt the derivative of a phasor in R. We know, and this is gonna be the same that in here, because it's the same geometry. It's just that we move the coils by an angle, but the inductance is not gonna change for that because they maintain the same 120 degrees. Now what is gonna change is when we do the mutual inductance between the rotor, because if you remember, we are gonna still have LSR, But if you remember, to go from the stator to the rotor, we added an angle, but to go from the rotor to the stator, so we know that we are gonna get here the stator phasor. Just like here, I'm sorry, I wrote it wrong here. We got here the rotor phasor because this is all in terms of R. So here we are gonna get the stator phasor, but because we want to go to the from the stator to the rotor, we need to add an angle. We subtract an angle. So if we are going from the rotor reference frame to the stator reference frame, then we need to add an angle. And if we are going from the stator reference frame to the rotor reference frame, we have to subtract an angle. Now, this is a quick way of figuring out the voltage in the rotor, but you can do the same and all the same calculations that we just did for the rotor and prove that this is true. So, for our model of a wound rotor induction machine, we have figured out the voltage in the stator. We have figured out the voltage in the rotor. And we have some assumptions where we said that M is equals to this. Now we have another M. I'm gonna go MR for neutral in the rotor, but it's gonna be basically the same. The peak in the rotor square, and we're gonna have our LSR, that is our peak in the rotor times our peak in the stator. And remember, this is the peak number of turns. In another video, I explain where we came for this. And finally, we have ls. Okay, so for now, this is what we got to model our wound rotor induction machine. I hope this helps.